Hello everyone, I'm Dong from International University. My topic is the introduction of the Korea EU educational program, the double degree in hydromathematics. This program is supported by the Ministry of the Education, and this program is planned for double master degree for the master students from Korea University and EU University. This is the table of contents of my presentation. First, I introduce my program, and second is the composition of the consortium, and third, operation of the dual degree program, and fourth is the activities of the program, and lastly, I present my future plans. First is the introduction. The hydroinformatics. The hydroinformatics is a concept with the some information and communication technologies with the application for efficient use of the water. So general water resources and hydraulics and water supply system is included from hydroinformatics, and based on the some real-time measurement and data management and operation, it content included in the hydroinformatics. So based on the hydroinformatics, the double master degree student join our major, and the Korean and European country they develop these theories, and we want to import the workforce from the students using their talent for this majority. So you can see some background of the educational cooperation program, some nature, education, and cooperation, and manpower. So the university of this from international university, including some EU university, we are joined to Euro Apply Plus. So we support some scholarship for the students. And I introduced the composition of the consortium. You can see the Incheon National University and Seoul National University and Chungbuk National University from Korea side, and for EU, the University of the Sophia Antipolis and UPC and BTU and Warsaw University is the member of the EU party. So for Korea, the Incheon National University is the main partners, and for EU, the University of the Sophia Antipolis is the major partner in the EU side. And the K-Water and ICH and other some company support the internship program from Korea, and for EU, the DHI and Akbar and Suez also they are managing the internship program for the students. And there are annual some educational program from Korea, the Hydro Asia and Hydro Europe in EU. And there are so many activities to promote the relationship between the Korea and Europe. So this program is start from the Professor Choi and Professor Philip. So International University and this university they are collaborated and developed this program, and other universities from Korea and Europe and also join this program. And every year we have some regular meetings, and there are many conferences and some meetings and seminars. So we can join together and we can share our knowledge, and we can make some educational curriculum and operating some educational program. Third one is the operation of the dual degree program. So you can see some details of the support party. The Ministry of the Education supports the scholarship to the international university, and the European Commission also supports the fund for this university. So we have our party, like our department and some international peace and graduate school of the INU support the student living and their administrative process. And the Seoul National University and Chungbuk National University, they are support the student recruiting, and for UNSA side, the UPC and BTU and Warsaw and other consortium university also recruiting the students, and they are engaged in our exchange program. So you can see the many MOU for operating this program. From 2006, the MOU is established for exchange students between INU and UNSA. And from 2009, we officially we operate the student exchange process with the transcript recognition. And 2014, we had the MOU for joint dual degree in all participant organizations. And you can see some details of the student exchange during 4 semesters. For Korean students, they enter the university with a master's degree. At the time, they study in their home university. And second or third semesters, they exchange to the Europe universities. So they receive some classes for their higher project measure, and they can join to the internship program in the related companies. And last semester, they come back to a home university, so they prepare their thesis and their presentation to the both university. So finally, they can get a double master degree between Korea and EU. And program schedule is like this. From Korea to EU, the first semester is start from May, and their first semester in Europe is start from September and finish is the next year June. So during the 10 months, they receive the many major course and field trip and research progress. So, and also they are participated in hydration and Hydro Europe. From a European student, if they come to Korea, they can start their first semester in international university from March. So they can finish their second semester of the Korea University in December. So during the 10 months, they can reach the 2 semesters for satisfying their dual master degree. This is the Euroaccord Plus curriculum. So, in general, some European students can receive the 4 semesters in Europe. But if they want to come to Korea International University, they can join the 2nd or 3rd semester. And there is an educational curriculum in International University. There are all subject is related with hydroinformatics. So 2nd semester is the basic course, and 3rd semester is the application process, including the internship program. And we International University providing some language program. If the European students come to Incheon International University, they can apply the Korean language class. So we support the Korean language class from International University, and when the Korean students go to the Europe, the European University also supporting the language program. And next is the main activities of the program. 2009, we start the first program. So 30 students are involved in the exchange, only 1 semester of program. And from 2014, the student can receive the double master degree. So International University and Chungbuk National University students are joining this program, and they can also receive the degree from EU university. And third project it also starts from 2018. We scheduled to 12 students who will enter this program. And you can see some awarding master degree. The recruited students can apply double master degree, and they should prepare their thesis, and they can depend to the both university, the European side and Korean side. We can support some online pre-entry system, so they can depend from this like that. And we promoting our program using the poster and some journal report. So many participant students already submit their some experience and their knowledge about this program. And there is a web page and online platform. So all students can join this web page, and they can share their experience. And we also support the internship program. So some European students has their internship in K-Water, in ICH, and if they write their report like this, they can receive the research credit. And this is the pictures in field trip in Korea. We contact to some engineering company or K-Water, and we support the field trip. And some in the EU part also support the field trip and some class from Europe, and they are supporting some internship program. So this is the Hydro-Asia and Hydro-Europe. So in Hydro-Asia and Hydro-Europe, they can teamwork together. So if they choose their subject and title, they can co-work research, and the final date they should present their outcomes. And next is the final is the future plans. Actually, our program is to support the students who get a double master degree. But if we extend this program, we can support the doctoral degree for the applicants. So the main university is for European side, it's the Ethiopia enterprise. So we wanted to asking, and we wanted to develop a more nice program for get a double degree for doctoral, and we want to strengthen our internship program to the after the students they receive the master degree, they need to get a job in related fields of the hydroinformatics. So we want to enforce our relationship together, and maybe this program will be finished 2022. So after that, we don't know we can continue this program, but we have to promote, and if we have the many graduate students from our program, we can continue that program. Thank you very much for your attention. Next presenter is the Eunbi Hong from Chungung National University. Her topic is the flow analysis of urban area using XP3 in Seongnam Stream in Cheongju, Korea. Please give a big hand for her. And the presentation time is 10 minutes. So if the 10 minutes, I will let you know the time.
Hello, I'm Eunbi Hong. I will start the presentation about flood analysis of urban area using XPC. It's table of contents. its introduction. Urbanization caused like this, and climate change caused by global warming is becoming a huge problem internationally. Especially South Korea has suffered from severe flood damage. It's because of the frequent occurrence of regional heavy rain. Therefore, in this study, the exact cause of flood damage near Sangnam Stream in Cheongju is analyzed, and the degree of damage is simulated to verify the accuracy by comparing it with the actual one. And application of the same in study area. First, study area. The area consists of a large shopping mall and parking lot with a Cheongju cargo terminal and a car charging station to the south, while Sangnam Stream flows to the east. And rainfall data and events. On July 16, 2017, the North Pacific anticyclone and the low temperature dry air pressure correlated in the central part of Korea, causing heavy rains exceeding 300 years flood frequency. The maximum rainfall of 1 hour was 86.2 millimeters, and the cumulative rainfall was 290.1 millimeters. In particular, a review by the Cheongju Observatory found that more than 100 years frequency of rainfall, which is the design frequency, occurred in the case of the total duration, and more than 500 years frequency of rainfall occurred in the case of 3 to 6 hours of duration. In order to analyze the exact cause of flooding, modeling was conducted by categorizing it into two categories. Input data. First is drainage area. The first priority for the XPCM input is to determine the sub-basin area of each node. Second is width of sub-basin. The sub-basin width is only used to track flows using runoff and kinematics waves of routing methods, so applying value above 0 does not affect flood volume. Third is slope. In the case of the slope by sub-basin area, the slope is calculated by division into the length of the pipeline, assuming the start point of sub-basin as the start point of manual and the end point of sub-basin as the manual end point. Fourth, percentage of impervious. The rate of impervious area is used to divide the sub-basin area into impermeable and permeable elements, respectively. 5. Calculating loss for determining effective rainfall. Surface stretch. It is assumed that no surface runoff occurs before the ground of permeable and impermeable regime is sufficiently surface storage. Within the same model, surface storage is used as a verification factor to compensate for the runoff volume, and the surface storage value represents the runoff volume for the rainfall of various rainfall events. And Manning's and the runoff coefficient of Manning is applied to reflect the flow resistance according to the surface conduction of the subbasin. And the following are the surface roughness coefficient value presented in the work design of water resources. This was classified relatively suitable according to domestic conditions. The roughness coefficient value were classified and applied to impermeable areas and permeable areas. And in the case of impermeable areas, 0.012 was considered to be asphalt pavement areas in commercial area. In addition, 0.030 was applied to the permeable area, considering that there was no farmland and the area where the trees were aligned and the area was grassy. And building a same model. First, building a pipe network, same supports three modes, RNF and SAN and HDR. The pipe network of the areas studied are as follows. The blue circle is the pipe network are the points of discharge into the stream. This is link data and node data. And rainfall data, input rainfall in the area covered by this study is from 6 a.m. to 12 p.m. on July 16, 2017. It rained until 12 p.m. Its rainfall data was entered every 10 minutes using Cheongju AWS data. Its rainfall time was simulated in the same way as the actual rainfall time, not at random. And third is results and discussion. When modeling only the pipe network map, there was no flooding in the 2D flooding footprint. There was no manners in which most of the maximum water level line rose above the ground level. The following are the results of modeling only for pipe. Figure 3.1 shows the result of the time when the rainfall was the highest around 7:40 a.m. The pipe network near the left is the largest of all the links, so it is marked in red with a large discharge, not a flood. After putting in the river water level, the flooding began to appear on the flooding footprint. Figure 3.3 is the result of putting elevation 37 meters, the highest river water level at the time. Compared to the photos of the actual flood damage, The results are similar, based on the fact that the depth of flooding near 롯데마트 was about 0.9 meters. The results are similar to the photos of the time when most of the water was flooded around the street. And figure 3.6 is the result of 740. It can see that the manor near the stream is almost flooded. Figure 3.7 is about 1130, and it can see that most manors are flooding. The maximum flood depth was simulated to be about 2.5 meters near the stream and about 1 meter near roads and shopping malls. This is just to be similar when compared with the picture at the time. Finally, conclusions. Heavy rain exceeding 300 years frequency occurred due to the stagnation of the seasonal rain front. And this study was modeled in two ways: when external water was not entered and when entered, to compare and analyze whether internal or external water were more affected, because both factors caused flooding in a combination. As a result, when the modeling on the sewer network, there was no major problem with the sewer pipe network. Although the maximum water level line was close to the ground elevation, it was confirmed that there was no flooding. While when the water level of the river was put in, the flooded immediately. The inability to properly drain the flooded water can also cause flooding. However, the flood damage would not have been so great if there was no rivers or if the water level of the river had not soared. In other words, it can be just that although there was an impact from internal water, it was more affected by external water. Resort area are low-lying and paved area for topographical regions. It can be interpreted that the water was not properly drained when the stream was flooded, and that the water remained intact due to the low rain. Next, we check the extent of the damage analysis. Analyze the XPCM and the actual situation at the time to see if the analysis was done well. And the depth of flooding near the stream was about 2.5 meters, and it was judged that the results were similar to the actual conditions because it actually overflowed across the embankment to the entire surrounding area. After checking the flooded area, it can see that the entire area was flooded. In fact, modeling results also showed that
please summary your presentation.
uh, Modeling results also showed that the area was flooded equally. And structure and police measures should be taken into account to prevent flood damage caused by overflow stream. Although the flooding was caused by a very heavy rain of 300 years frequency, it is hard to tell how often the damage will occur in the future due to continuous climate change. Therefore, I think we should take active structure and police measures to reduce the damage, even if we cannot completely prevent it. Thank you.
Thank you, Mi-hong. Do you have any question from this presentation? question?
한국말을 물어봐도 돼요?
네, 괜찮아요.
25페이지 보시면요. 그 2D 모델링 할 때 바운더리 더 확장해봤어요? 2D 모델링 바운더리?
2D 모델링 바운더리를 더 확장해도 그 옆에 지방고가 제가 자료가 없어서
자료가 없다고요? 지방고 자료가?
네. 그러니까 각 노드의 지방고 자료는 있는데 그 주변 확장 자료가 없어서 저 부분만 2D 모델링을 들었어요.
Because of the limitation of the time, so if there is no question from here, maybe we can continue some other presenter. Thank you. Next presenter is the Suwon Lee from International University. His topic is the analysis of the rainfall runoff in mountainous area and flood impact extent using micromodel. Please give a big hand for him. 되시죠? 잘 돼요?
안 되는.
직접 해야겠어. 이걸로 해.
여기서 넘겨줄게요.
네. Hello, my name is Suwon Lee. I will start my presentation. My title is Analysis of Rainfall Runoff and Flood Area Extent using the micromodel and proposal of mitigation measures. And I set up the contents as follows. Next. Sorry. So I would like to proceed with the results as follows. I use microsheet to calculate the runoff of the mountain area and microtwinion FM to calculate the flooding. The study area concerned the Bar River catchment. In November 2015, the Bar River had a serious flood with expensive damage on the infrastructure. Low Bar subcatchment is selected as the research area due to the dense residential areas and living facility and most affected by flooding. So I choose two catchments. The two catchments are located in the lower Bar Basin. Catchment 1 area is 4.69 and catchment 2 area is 4.66. and I collected rainfall data. In addition, 1 and 20, 10, 20, 50, and 100 years probability rainfall data were also collected to compare with 2015 rainfall. So I create many input data for microsheet. At first, I create catchment, based on information about river catchment, such as area. Slope and land use were analyzed using GIS, and 2 catchments were constructed. For more reliable rainfall runoff simulation, a DEM with 5-meter resolution was used in the study. And next, since the elevation of the streamline created through the DEM is influenced by the surrounding terrain, it is difficult to obtain the correct elevation and slope. Thus, the DEM modification work was carried out for each subcatchment. And next is land use map. Land use data held by NIST Sophia Antipolis University is produced in a 100-meter resolution. However, in this study, the analysis is conducted using the 5-meter resolution DEM, which require rebuilding of land use data. ArcGIS was used the rebuild land use map, and land use map was rebuilt by dividing it into 3 zones: grass, forest, and urban, based on satellite images. And next is many number map. Many number are required input for microsheet, has different coefficient value for each land use map. Based on land use map, streamline was added the 3 types of grass, forest, and urban to establish many number input data. And next is soil type map. Soil type was also analyzed using values for the NIST river basin, use the Kwangma based on land use type. However, a problem occurred in the simulation conducted without micro-level. The first problem was that the accurate runoff was not calculated. Second, streamline flow was stopped and an anomaly water level point occurred. This is because the microsheet alone cannot create the channel through which water can flow, and because the time to calculate the runoff is long. It takes a long time to collect water at the final outlet. So this result requires a coupling with micro-level. So I created micro-level data. And I use micro-Twinion FM for 2D simulation. So I did some work for micro-Twinion FM simulation. The first one is DEM modification. The DEM produced by the NIST Sophia consists of excluding roads passing over rivers. In reality, because the flow of the river is affected by the covert under the road, the DEM must be modified to look like the reality. Therefore, the DEM was corrected by referring to the elevation of the road in the downstream area of the 2 catchments. And the catchment 1 was also corrected of the downstream streamline elevation. And mesh data was created for micro-Twinion FM simulation, and covered were input as in the reality. So mesh data was created using 1-meter resolution. And catchment 1 set 2 covers under the road. Catchment 2 set up 3 covers for the upstream area and downstream road. First content is analysis result. The discharge of catchment 1 was calculated based on the discharge of the previous study for discharge. In the previous study, analysis was conducted based on the 100 years frequency, resulting in the discharge of 8 cubic meter per sec for 0.75 square kilometer. So I set the expected discharge for catchment 1 to 50 cubic meter per sec. So the soil type value was modified for the expected discharge, and when I was 60% lower than the original value, a discharge close to the expected discharge was obtained. So each probability rainfall and observed rainfall were analyzed using the soil type value of 60% down. As a result, the 100 years frequency of catchment 1 was 47.084. The 100 years frequency result of catchment 2 was analyzed as 64.581. And the discharge for observed rainfall data was analyzed as 55.923 cubic meter per sec in catchment 1 and 71.753 cubic meter per sec in catchment 2. Microtransition FM was simulated using the discharge analysis through microsheet, and the results were as follows. This is the 10 years return period and 20 years return period. And this 50 years return period and 100 years return period. And this is observed rainfall result, catchment 1. And this is observed rainfall result, catchment 2. This is comparison of the result. In 2015, more rainfall occurred than the 100 years frequency. The 2015 rainfall is catchment 1 was about 93% higher than the 100 years frequency. And the 2015 rainfall in catchment 2 was about 70% higher than 100 years frequency. The analysis of catchment 1 showed that the main cause of flooding in the catchment was due to the lower capacity of the covered outlet compared to the flow which can be conveyed by the stream. If the conveyed flow rate is calculated under the assumed of the standard diamond shaped channel, and by applying the average flow rate of 2 meters per sec, the maximum flow rate of 46.225 cubic meters per sec can be conveyed by the channel. However, only 36 cubic meters per sec can pass through the cover if the downstream boundary conditions are not applied. If the size of downstream cover is increased, the flooding upstream could be reduced. The flooded area of the catchment 2 analysis basin are mainly playground and wetland that correspond to the upstream of the basin. The playground and wetland are located lower than the surrounding area. And finally, conclusion. The result of this study showed that in both study areas, the large amount of runoff generated in the mountainous upstream area was higher than the design conveyor capacity of the downstream covered outlet. This study showed the result of the simulation without setting the downstream boundary condition. If the water level of the Bar River is set and modeled as the downstream boundary condition due to small difference between the Bar River bed elevation and outlet bed elevation. The runoff caused by the rainfall in the mountainous area will not be discharged and future damage will be caused. As the first measure to prevent flooding in this study area, the gate and pump of the spillway are installed, and the amount of runoff from the mountainous area is rapidly discharged. This method is expected to have a greater impact if the riverbed level is lower by bar river maintenance, which will cause the water level to be lower. The second measure would be to prepare for flooding by creating flood storage areas in playgrounds or parks corresponding to lower lying area, such as in catchment 2. Thirdly, if artificial streams are built in the border area of mountainous area and residential and commercial area to create waterways, it will be possible to prepare for flooding as rainfall at the beginning of the rainfall event can be discharged quickly. In the future, by applying measures such as flood flow monitoring of small mountainous catchment stream, construction of riverbed cross-section based on survey, construction of hydrological data by flooding measurement in each small mountainous catchment, or construction of flood extent map for recorded historical flood event. The accuracy of the result from the simulation will be improved, and through a more precise flood analysis, the flood risk prediction to industrial and residential area will be more accurate and reliable. Thank you.
Thank you. Do you have any questions for this presentation? I just short question for you.
Yeah.
When you install the gate and pump on your flood model, did you consider some coefficient for that facility? In your conclusions, there are some contents of the spillway. There are some gate installation and pump installation.
I didn't try it yet.
You didn't try it.
Yeah.
But why the content is included in your conclusions?
Because I just think it's more. 일단 저거를 그냥 대안으로만 내세운 건데 저거에 대해서 아직 시뮬레이션을 못했거든요. 왜냐하면 아직 마이크 트윈이나 FM에 대해서 이제 펌프나 스피드웨이 같은 거를 넣고서 아직 하려면은 좀 더 이제 모델에 대한 공부도 필요할 것 같고 해가지고 일단 저거는 대안으로만 냈고 그거에 대한 아직 시뮬레이션을 못한 상황이에요.
네, 알겠습니다. 네, thank you. And there are two remaining presentations from Jean-Baptiste Nicole and Guillaume Petri. So, but they are stay in the France, so they just send their video presentation. So we can play their presentation. And first, the presentation from Jean-Baptiste Nicole. He studied in University of the Dystopia Antipolis. His topic is impact of the transient phenomenon in water supply network and solution to limit it.
Hello, I'm Jean Petri and I'm going to speak about my project on the impact of variability of rainfall information on extreme hydrological statistics. The goal of this project is to evaluate the accuracy of different hydrological models by associating it with different rainfall data. Firstly, I will speak about the hydrological model I used, which are GR4G and GR02G, and the data I had at my disposal. Then I will speak about the rainfall accuracy, which I will try to associate with the results of the two hydrological models. Finally, I will speak about the efficiency of the models to reproduce QV10, which are decennial daily flow. Water resources are a major concern, either it is about low flow phenomenon or floods. The last decades, floods have caused human losses and collateral damage amounting to several billion euros, and I think it's important to have a better understanding of the functioning of hydrological models and to know more about the importance of accuracy of rain data. I use two hydrological models, GR02G and GR4G, which are global conceptual models. A conceptual model is the simple representation of reality and does not try to reproduce as accurately as possible physical laws. The function objective I used is the KGE on Q and 1 divided by Q. The KGE on Q, we try to produce the floods, and the KGE on 1 divided by Q, we try to produce low flow phenomenon. On the two models, we have a production function, which is used to determine the quantity of inputs which go to the output of the model, and we have a transfer function, which determines the time repartition of the water. We can see several differences between the two models. The GR02G model has a snow reservoir, and it has a balance sheet which allows to make correction at the end of the model. And the GR4G has the UH1 and UH2 functions, which allow to make a more accurate transfer function, and it has the F function, which simulates the exchange between a watershed to the exterior. We have several rain data at our disposal: the rain radar COME4 at a scale of 1 km², the rain saffron at a scale of 64 km², and some rainfall sections. About watershed, we have 691 watersheds in France, which are mainly rain watersheds. But we have snow watersheds too, uniform watersheds, and Mediterranean watersheds. Firstly, we have to evaluate the difference between COME4 and saffron. But COME4 is at 1 km² and saffron is at 64 km². So it's possible that all the difference between the two series are because of the scale. So I created a third series which will serve as a reference. To evaluate the accuracy, I use the Nash criterion, which is able to evaluate the proximity between two series. On the figures, each point represents the interannual accumulation of water on the location of an rain section. To evaluate the accuracy of the COME4 and saffron series, we use the rain gauge stations as a reference. We can see that the COME4 is very close of the rain gauge, but it's not the case for saffron. We can see that this difference is partially explained by the scale if we compare the COME4 and the COME4 64, but it's not enough to justify so much difference. To look further into the different sources of rain, we put the data at the scale of a watershed. So on the figures you can see each point represents one watershed. We can see that the COME4 data is inferior to saffron, but it's caused by the fact that COME4 doesn't take into account snow data. So for watershed at less than 500 meters, saffron and COME4 are really close, but it's not the case for watershed at more than 2000 meters. Indeed, there is more snow at high altitude. But we will keep the data. Indeed, I think it will be interesting to see how the hydrological model will be able to adapt to this lack of information. We have now an idea of the accuracy of the different rain data. So now we can make a comparison between GR4G and GR02G. All the rain data we used have a corresponding flow data from measuring station. We use the Nash criterion to evaluate the proximity between the output of the models and the reality. There are several statistics we can use to evaluate the proximity between the reality and the output of the models. There is a median of Nash on daily flow, a median of Nash on seasonal flow, and the spatial Nash on the different statistics. And we can see for each model that there is not so much difference between Safran, Comefor, and Comefor 64. It's because all the watersheds are represented on these figures. Indeed, we can see the difference between the watersheds which are at more than 2000 meters or the watersheds which are little or big. So we will separate the results between different categories, and I will only show you the meaningful one. On these figures, we can see only the basins over 1,500 meters above sea level. We can see that there is no so much difference between Comefor and Comefor 64 km square, but there is a slight advantage for Safran. It's probably because the snow data is not taken in account in Comefor, but the difference is really slight. This time, the figures show the watersheds of less than 20 km square. We can see that Safran is slightly inaccurate comparing to Comefor. We could think it's because Comefor is at a scale of 1 km square and Safran is at a scale of 64 km square. But as you can see, Comefor and Comefor 64 doesn't seem that much different. The two following figures show the results only for Mediterranean watersheds, and we can see that Comefor is slightly more accurate than Safran. Until now, we tried to see the accuracy of the models to reproduce great length of data, years of data, but now we want to try to see the effectiveness of the model to produce floods, only floods. In this section, so it is not necessary to compare the results between Safran and Comefor. We are only interested in the effectiveness of the models to reproduce a quantity of daily floods, and Safran rain series is picked because it has the longest period. The figure represents the comparison between the medians of the simulated decimal daily flow of SHIREG, GR02G and GR4G according to the different specificities of the watersheds, hydrological regimes, small, large surface, low and high altitude. The watersheds where the two hydrological models have the most difficulty reproducing SHIREG are the uniform watersheds with, for SHIREG, GR02G and GR4G medians of 4.6, 2.4 and 2 millimeters respectively. It is interesting to note that for snow watersheds, the GR4G model correctly reproduces SHIREG, unlike GR02G. This could be explained by the use of semanage, a more complex snow module than the one integrated under GR02G. It has been highlighted that the variability between the Safran and Comefor rainfall series is not negligible, but this difference, which is to the disadvantage of the Safran series, is on average more a standard deviation than an overall underestimation or overestimation. With regard to the modeling of low water, balance and seasonality concepts, the results are on average slightly better using the Comefor rain series, with the exception of certain values of the snow watersheds. Indeed, the Comefor series do not contain solid precipitation for high altitudes, but the model managed to obtain satisfactory results by compensating the parameters, especially for GR02G. But depending on the model and depending on the choice of statistics to be reproduced, the rainfall series to be favored is not the same. For example, for the GR4G model in watersheds with an altitude of more than 1,500 meters, the Safran series is preferred to be reproduced the balance sheets, while a monthly low water criterion like the QMNA5 will be better with Comefor series. It is therefore difficult to be able to conclude in an absolute manner on the choice of the pluviometric series, especially with an improvement on average as low. On the other hand, it would seem that the use of COMEFOR data tends to improve the simulation of the flow of man-watersheds, less than 20 km², as well as the simulation of Mediterranean watersheds more significantly. Concerning COMEFOR 64 km², the results are inconclusive because no significant difference could be highlighted. Therefore, using data with a resolution of 64 km² is not considered to have a significant influence. Regarding the evaluation of the two continuous hydrological models and the simulation of a daily flood quantile, the performance of GR4G and GR02G are satisfactory. Thank you for your attention.
This presentation is presented by Guillaume Petry. The title is The Impact of the Variability of the Rainfall Information on Extreme Hydrological Statistics. So, the Guillaume Petry is involved in the double master degree program in the last year, and this content is the thesis title of his master. So, maybe if you have any question to this presentation, you can connect to Guillaume Petry by his email. So maybe I can give this information to you after this session. And next is the presentation from Jean-Baptiste Nicole. The study of the water hammer in existent, the phenomenon. So please play.
Hello everybody, I'm sorry. I'm not here today, but I will do my best to make you. Hello everybody, I'm sorry. I'm not here today, but I will do my best to make you understand my presentation. My name is Jean-Baptiste Nicole, and I will explain you my choice to protect waternet in south of France against water hammer. To realize it, I did 2 studies. These studies fit into a vast financial program to support agriculture despite global warming. In this map, you can see the location. These studies are linked. The first study Louvière is an existent net which is reinforced by a pipe in 600 mm. This is in purple in south of the map. And the second one will be built. This net is in green on the right of the map. Before to go in detail, I will explain you what is a water hammer. To be simple, we can define
To a better concern.
However, is reinforced by the first study Louvière is an existent net which is reinforced by a pipe. The first study Louvière is an existent net which is reinforced by a pipe in 600 mm. This is in purple in south of the map. And the second. Hello everybody, I'm sorry. I'm not here today south of the map. And the second one will be built. This net is in green on the right of the map. Before to go in detail, I will explain you what is a water hammer. To be simple, we can define it like a system which has not returned to its steady initial state. If nothing is realized to fight it, the pipes can explode or improve. With this parameter, the law wants no negative pressure in a safe water system. In my case, I am in a raw water system. We can admit -3 meters in pressure. With these elements, we will determine the protection to use. We have bypass circuit, water hammer hair vessel, flywheel, and this protection can be complete with a local protection. Water hammer valve for overpressure or depressure, a link between sonic air purge and inlet valve, or a free surface water volume. After choosing the protection, in function of the length, the type of the net, we will size it. To calculate it, it's possible to use a computer modeling or a Bergeron approach. In my case, I use settlement software which use graphic method to solve a water hammer. To understand it, I can show you some existing protections. On the left, we have a flywheel where the wheel will decrease the first wave of the pressure. On the right, we have an air chamber which can store or release energy in function of the wave pressure. With them, we can use a trip function valve or a link between sonic air purge and inlet valve to limit the pressure in the net. For example, in the high point on the net, it's used to decrease the pressure. On the right figure, we have the blue net, which is Louvière, and the black net, which is mirable net. When we see the left figure in the black cycle, on the top we have in yellow the mirable net, and in green the Louvière net. We can notate two differences between them. The difference of altitude between the pumping station and the reservoir in mirable net is approximately 100 meters, while the Louvière net has the double. The second one is the length of the net is important in the Louvière, whereas the black one is little. The first study will be the Louvière, and I chose an air chamber in this case. To dimension it, we need to calibrate the informatic model. To do it, we enter the pump's curve, decreasing curves, and I will modify the operating points to have the desired flow. The increasing curves are the network curves. The differences between them is the simulation conditions. The green one is the minimum conditions, which is let the bed pressure. We have rugosity equal to 0.5 millimeters, the tanks in the lowest level, and the maximum consumption in the net. The blue one is the maximum condition, which is let over pressure. We have rugosity equal to 2 millimeters, the tanks in the highest level, and no consumption in the net. In this case, the operating points is similar with the intersections of curves. The maximum point is higher, so the results will be better, because we simulate a worst case. But it doesn't matter, I will explain it later. To protect the net, we need to determine the worst case of water hammer. Due to the presence of the drive at startup, the disjunction cases will be studied. The figure on the left is the maximum disjunction, and on the right is the minimum condition, following the adoption profile. It's possible to see the worst case is the minimum condition, so on the right. Indeed, the net knows more the pressure. But for you to understand it, the rail line has a limit to do not exceed. When the dark blue line stays inside, the net is protected. When the dark blue line is outside, the net is not protected. The dark blue line, in fact, is the maximum and minimum of pressure due to the water hammer in the pipe. By iteration, we will determine the minimum V0 so that we know no pressure problem in a problematic point. This V0 value will let determine the maximum volume of air in the air chamber. Despite this V0, the furthest point knows some bed pressure. This is on the left graph. To avoid oversizing, we need to put in the place a local protection. On the right graph, we see the reduction is protected with this V0. When we put in place an air inlet valve at the furthest point, we have the left graph. Finally, the net is protected because, like we saw in the previous page, the net is protected in the adduction. In the right graph, we take the maximum value of volume in the air chamber. This maximum volume we take with a safety coefficient, and we will determine the air chamber to put in place. In this second part, we will study the mirrorable net and the use of the flywheel. As seen previously, we calibrate the model. Our operating points are good, so we can continue. Same things, we have a drive at startup, so the disjunction cases are studied. Like we can see, we know the pressure on the adduction, on the left graph, and in the furthest point of our net, in the right graph. By iteration, we will determine a PD square. It's a value in Sydney to determine the necessary inertia to put in place in the flywheel in function of the problematic points. The inertia to add, finally, is 42.5 kilogram multiplied meter square. With this inertia, we can determine a type of flywheel from an abacus. It's a table in the bottom of this page. And in the graph, the first graph in the adduction, we don't have the pressure, we have no problems. And in the second graph, we don't have problems too. Finally, we need two protection difference for two different nets. The first one, the Louvière net, we need two air chambers of 11 meter cubic and one air inlet valve. This inlet valve will be complete with an air purge. And the second one is two flywheel. This flywheel will have a diameter of 900 millimeter and will have a weight of 418 kilograms. In conclusion, the choice of flywheel is due to the difference of altitude between the reservoir which inlets water and the reservoir in the outlet of the net. In fact, the water hammer phenomenon is very short in time because the outlet reservoir will absorb the phenomenon. So the flywheel will help to reduce the water hammer velocity so that the reservoir takes up the pressure. Furthermore, for the exploitation, the maintenance is easier. In the case of Louvière, the net is complicated. We have a high difference of altitude and a very long net. So the air vessel solution is easy and not expensive for it. Thank you for your attention.
I'm especially thanks to Jean-Baptiste Nicole and Guillaume Petri. And maybe they just only sent their video presentation to this session. So we can have if we have some questions, we can directly connect to him by email. Thank you all of us, and I want to close this session, and we have to lunch time, and there is opening ceremony at 1:30 in Grand Ballroom. Thank you all of us. Thank you.